Okay, good morning. Time to start with our lecture for today. I'm going to ask you to turn off your screen, your computers. Also to pay attention to what we're going to be discussing today. As you already know, we are having our second exam on Tuesday. So my plan for today's lecture is to basically go over the dual theory material again, which is going to be part of your exam, and also complete the material. I think we have only one more topic to cover at the end of this lecture. And after that, we're going to look at the review, which is already posted on Track. And we're going to discuss some problems from the homework that I posted on Tuesday. And then I'm going to basically answer some of the questions that you might have for the exam. Okay? Is there any questions at this point? I also noticed that some of you are not, I looked through the homework. I don't have the grades for the homework yet, but I'm going to have them ready tomorrow. If you want to pick your homework, you use it to study for the exam during the weekend. You can stop by tomorrow, your homework will be graded. But I noticed that some of you didn't complete some of the problems, and I was wondering what happened. Didn't have time, or you didn't understand what you were trying to do, or the problems were too long. Can I get some feedback from you?
All of the above.
All of the above?
Yeah.
Well, I thought that since you had spring break, I thought you were going to be working on studying for the homework. But that was not the case, actually. Some of you were able to work on all the problems, but I would say half of you just tried, but I don't think that you put a lot of time on the homework. Even though you had that spring break to try to work on it, do you have a lot of exams this week, or? Okay, so that's something else. I assume. I heard that some of you are having a couple of exams this week. But what I'm worried about is I don't want that to affect your performance on the exam. So I posted the solution. You can take a look at the solution. The material is not hard. If you have questions, just let me know. It's just, once you understand what you're supposed to do, you should be able to complete the problems. Something that I noticed, the homework asks you to basically formulate and solve the problems. I would not ask you to do that in the exam. So basically, you can assume that you have the optimal tableau for some of the sensitivity analysis problems. You can assume that you have the optimal tableau, the solution, and start from there. So find the ranges, be aware of what does ranges mean. So if you go above them, you know that your solution will change. If you are within the ranges, then you know that the optimal solution will still optimal. That type of thing. And also, I'll go over those details in the review. If you remember, we also discussed how to get the sensitivity analysis report from the Excel. So if you can look at the report, and basically based on the report, I can ask you some questions based on that report. So you should understand what that report means and so on. Okay? So just to give you an idea of what type of question you should expect in the exam.
So is Excel going to be on the exam at all?
No, I will provide you with the answer of the table. You don't have to use Excel in the exam. Okay? But just understanding what that report means, that will be part of the exam. Okay, so this is what we covered last Tuesday. We started talking about the dual theory and how the dual of a linear programming problem can be useful when you have certain type of problems. So if you have a problem that have multiple constraints and you want to change that problem using the dual to have less constraints but more variables, that can help you to improve the solution time how long it's going to take to get the solution. So far, your problems, especially the ones that you solve using the computer, were very fast. You get the solution very fast because those were very small problems. But I'm thinking of giving you an example maybe later in the class in the semester, in which you will see that if you have a larger problem, the computer will take a lot of time to get that optimal solution. You're talking about, there's some problems that can take you like 3-4 days of computer power running in order to get the optimal solution. So most of the time, if you're dealing, let's say, with airplane traffic, that type of problem in which you want to find the optimal schedule for your airplane in this particular airport, that will take a lot of time. Like if you're dealing with, I don't know, 1,000 airplanes in an hour, if you want to get the best schedule to land those airplanes in your airport, in order to get that solution, that will consume a lot of computer power, and the slower the computer, the longer it will take. And so that's why it's very important to have these methods and understand the structure of the problem in order to be able to get the optimal solution as soon as possible. So based on that, the dual problem will give you a different structure for the same problem, but you know when you solve the problem, you will get the same optimal solution for the dual and the primal. So we defined the dual problem, and we discussed that they were closely related, and the optimal solution will be the same for both problems. And in our definition of the dual problem, we need to express the primal in equation form, which means that you need to change those inequalities to equalities in your constraints. And the key ideas for constructing dual, we went through these 5 ideas. We need to assign a dual variable. We need to construct a dual constraint for each primal variable. And the column constraint coefficient and the objective coefficient of the J primal variable respectively define the left hand and the right hand side of the constraint for the dual problem. The dual objective coefficients equal the right hand side of the primal constraint equations, and the sense of optimization, direction of inequalities, and the signs of the variables in dual are governed by the table, by this rule. Okay, so we use those ideas in this table to work on these examples. So we were able to formulate the dual based on the primal for a maximization problem. So this is the dual. You know it's going to be a minimization problem, and you will construct these constraints using the coefficients for each variable in the primal. Then we look at how to find the dual for a minimization problem. So in that case, you will go to a maximization problem, and you follow the same rules and ideas. And then we discussed one last example in which you had a unrestricted variable, and we discussed how to handle that unrestricted variable using this substitution. But at the end, you should be able to get a dual. And the most important part here was that you have these 2 constraints, and at the end, that will become only one constraint, because when you combine them, you can make them an equality. Okay, so in summary, and I pointed out that you can have this table in your formula sheet that will help you to find a dual from a primal, and you should expect a problem of that type in your exam. So I'll give you a formulation, a primal, an LP model, and I will ask you to find the dual for sure. Okay, so make sure that you understand how to get the dual from a primal. So if the primal is maximization, then the dual is minimization, and vice versa. Then we talk a little bit about the relationship between the dual and the primal. So changes made in the data of an LP model can affect the optimality and the feasibility of the current optimal solution. So this part of the lecture discussed the primal-dual relationship used to recompute the elements of the optimal simplex tableau. And this relationship formed the basis of the economic interpretation of the LP model and for cost optimality analysis. So the discussion were based on, we discussed the importance of the starting tableau and the optimal tableau in the simplex method, and how the identity matrix basically identify your basic initial variables. And then at the optimal, you know that the place in which this identity matrix was, and the optimal solution will provide you with an inverse matrix, and that inverse matrix is what you can use to find the optimal values for the dual problem. And we discussed two methods. So after this, to find the optimal dual solution, and these are the two methods, and we're going to refer back to this later in the class. So if you have the optimal tableau for the primal, you can find the optimal dual variables by using that tableau. So think about having the original problem, and you want to find what are the values of the optimal variables for the dual problem. So this is what the problem, these two methods are doing. You have two different problems or two different formulations for the same problem, the primal and the dual. If you solve the primal, you'll get some optimal solutions for the primal. These two methods will tell you, okay, you get the solution, you have the solution for the primal. I can tell you what are the solutions for the same problem, what are the decision variables or the optimal decision variables for the dual. Okay? So we go from using the primal information, you will get the optimal values for the dual values. And this is what these two methods are doing. So the elements of the row vector must appear in the same order of the basic variables listed in the basic column of the simplex tableau. So if your optimal solutions were x3 in the column, if you have x3, let's say this is your tableau, this is C, and this is the solution, and these are the x2, x1, this is 3, this is 2, let's say this is 15, the optimal solution. Then when you list this, what this is saying is the elements of the row vector must appear in the same order of the basic variables. So the order here is x2, x1. Okay? Because it's based on your basic variables column. If this were x2, x1, and x2, then this will be x1 and x2. So that order is important for method 2. Okay? That order is important. So we went through this example, we found the dual. Then based on the primal optimal tableau, we found the optimal dual values, which are y1 and y2. That is what we did using the first method. Okay, so we use the information from the primal optimal tableau to find the values, the optimal values for the primal, the dual variables. So optimal dual y1 and y2. y1 is 29 over 5 and y2 is minus 2 over 5. And I mentioned that one way to verify that this optimal solution for dual is correct. Does anyone remember what you can do to verify that this solution is correct? You found the optimal solution for the prime, right? And you know x2 correct. So you found x primal, you found x2 equals 12 over 5, x1 equals 26 over 5, right? And this is coming from here. So these are the optimal values from the tableau. x2 equals this, x1 equals this. Okay? So from there, in order to get this number, the optimal solution, if you go here, you use the primal objective function. So in that case is 5x1 plus 12x2 plus 4x3. That's the objective function. So if we substitute this number, this is 5 times 26 over 5 plus 12 times 12 over 5 plus 4 times 0 because x3 equals 0. This should be equal to this, 54 4 over 5. Because that's the optimal solution for the prime. Now, if you want to verify that these numbers are right, then you can come here. Back here you have the objective function for the dual. So that is 10y1 plus 8y2 dual. So if you take these values, y1 equals 29 over 5 and y2 equals minus 2 over 5, then this 10 times 29 over 5 plus 8 times minus 2 over 5 should be equal to 54 4 over 5. If these numbers does not give you this same objective function, that means that there's something wrong because it should be the same solution. Because the primal and the dual give you exactly the same optimal solution. Is that clear? Okay, so if I ask you to find the dual, and then I ask you to find the optimal values based on the optimal tableau from the primal, you can use one of the two methods. So if you use method number 1, you will get this and this. If you want to just make sure that your exercise is right and you got the right answer, you can always do this. Because you will have this already. So if you just check your values with the objective function of the dual, you will make sure that if that number is the same, you'll get the right answer. Okay? There's no way that your answer is going to be wrong. Any questions? Okay, so I'm just giving you that help, extra help, if you want to make sure that your exam is correct, at least an exercise similar to this one. Then we discuss method number 2. So this is method 1. Method number 2 will give you the same answer. And what I was discussing in terms of the order, you go back here. Here is where the order in the simplex basic variable is important. So if it is listed as x2 and x1, then you should put those values as within here, 12 and 5. Okay?
That would, like, if you were to mess up, that would only switch like the answer feedback.
It will depend on these values. Yeah, because you are multiplying that by, if it were the identity matrix, yes. Not that will depend on those. Any questions? And you know this is coming from here. So this is the final identity matrix. Okay? And we will discuss 2 extra problems in the review, basically looking at this one more time. And that basically tells you that this is important, and then you should expect something like this in the exam. Okay, so I'm basically giving you two problems already of what you should expect: the dual and finding the optimal from dual. Okay, so primal-dual objective functions. So we discussed this. We also went through the economic interpretation of duality. So I'm going to skip this because if not, I'm not going to have enough time to cover the review. I think I posted these notes, so you should have access up to here. And also, I posted the video. So, someone tried to open video? Open? Okay. So the video is also available. So let's start here. This is the post-optimal analysis. So in lecture 8, we dealt with the sensitivity of the optimum solution. We determined the ranges for the different LP parameters that will keep the optimal basic variables unchanged. And this is lecture 8 was the sensitivity analysis lecture. In this lecture, or this part of the lecture, we deal with making changes in the parameters of the model and finding the new optimal solution. And I'm going to refer back, just make sure that you make those notes. And I'm going to refer back to the example, the TOEIC example. In which we were trying to determine how many trucks, trains, and cars we should produce for each toy company. And we have the constraints for the operations and the number of hours per operation that we have available, and we were trying to maximize our revenue based on these revenues per product. So we have the problem, and if you solve this problem, the optimal solution, as we saw already in class, is $1,350 when you produce no trucks or no trains, 100 trucks, and I believe was cars, 230 cars. That's your optimal solution. That was the answer for that question, for those questions. Okay, so now I want to find the dual for this problem. So let me write the dual. So again, we follow the same concepts. We have a maximization problem, so now we have a minimization for the dual. So minimize z equals 430 y1 plus 460 y2 plus 420 y3. So you know that you need to define a dual variable for each constraint. Okay, so I have a dual variable for first constraint, for the second one, and for the third one. And from there, you just multiply the right-hand side times that dual variable, and you get the objective function. Okay, and that should be W, sorry. So you're taking the right-hand side and you're constructing the objective function for the dual using the right-hand side. Now, let's write the constraint. So subject to y1 plus 3y2 plus y3 greater or equal to 3. Then we have 2y1 plus 4y3 greater or equal to 2.
and y1 plus 2y2 greater or equal to 5. y1, y2, and y3 greater or equal to 0. And the optimal solution is y1 equals 1, y2 equals 2, y3 equals 0, and w equals, yes.
Why wouldn't I do
Oh, yeah. I skipped one step here, and I apologize for that. I needed to make this equalities first. So you remember the first step was to make this an equality and then move to the next. So let me see if I can construct this really quick. So x1 at the end is going to be the same answer. 2x2 plus x3 plus x4. I guess you don't need that one. Equals 430. Then you have 3x1 plus 0 plus 2x3 and then you need to add some extra constraints here. So at the end you will see that how that will become a y3 equals or greater 2, because this x3 now will become an extra constraint. So it will be y3 or y2 greater or equal to 0. Should be. It will be y4. y2 greater or equal to 0 and y3 greater or equal to 0. Okay, so that is why that becomes this. Again, I don't want to confuse you. So the first step you always need to do is to make this an equality. Remember? Because those constraints are less than or equal. Okay, so that's what I'm doing here. I'm adding those slacks and making those constraints equalities. Okay, once you have that in equality form, then you move and construct the dual. So from here, you go to here. So you start with y1 plus y3, y2 plus y3 greater or equal to 3. Then for the second constraint, you have 2y1 plus 4y3 greater or equal to 2. For the third constraint, you have y1 plus 2y2 plus 0 greater or equal to 5. Then you come to the slack variables. You have y1, you have no coefficient for x4 in your objective function, so that makes y1 greater or equal to 0. x5, you have no x5 coefficient here, so that makes x5 greater, y2 greater or equal to 0. And x6, you have no coefficients here for x6, so that makes y3 greater or equal to 0. So at the end, you know this y1, y2, y3 should be unrestricted.
But since you have those black variables, that will make them greater or equal to 0. Okay?
So I apologize for skipping this part, but this is important. Okay, and we have the optimal solution. So if you solve the dual, you know that you need to get the same optimal solution as the primal. So this is the solution for the primal. It's the same solution. You can solve it using the simplex method, but in this part of the lecture, we're not focusing on solving the problem. We are basically focusing on analyzing the solution. So if you solve it, this is what you're going to get, this value. Does anyone remember, we got these numbers at some point in the primal where we were looking at the sensitivity analysis. These numbers wanted to show it up somehow. Do you remember what those numbers mean? Those were the dual prices. So you basically were saying that if you added a extra unit of, I believe was X2, you were adding a unit of profit. So if you go back to the past lecture, you will see that these numbers show up. So those were dual prices. Okay? So the dual variables are telling you what are the dual prices for your problem. Okay, so let's look now changes affecting feasibility. So the feasibility of the current optimal solution is affected only if the right-hand side of the constraints is changed. By changing the right-hand side, what you're doing is modifying the available resources that you have. Okay? So right-hand side is basically the right-hand side of the constraints is telling you instead of having 60 hours, now you have 100. Okay? So that the feasibility of the optimal solution is affected only if you change that availability of your resource. You go from 100 hours of one resource and you go to 0, you know that the solution would be affected. And that could not be a feasible, your current solution or your current optimal solution might not be feasible anymore. This change requires recomputing the right-hand side of the tableau using the following formula. So in order to get the new right-hand side of the tableau in iteration I, you need to multiply the inverse in iteration I times the new right-hand side of the constraint. This is the type of formula that you need to put in your formula sheet. Okay? So to recompute the right-hand side of the tableau, you need this formula. Recall that the right-hand side of the tableau gives the values of the basic variables. Okay, so now let's look at two examples of changes that could affect the feasibility. So suppose that the company is increasing the daily capacity of operations 1, 2, and 3 to 600, 640, 640, and 590 minutes. So you want to know how will that affect your revenue. So let me go back to the problem here. Maybe it'd be good to have this formulation here. Maybe I can copy and paste that. Okay, so this is our problem. And what we're saying is, want to increase daily capacity of operations of operation 1, 2, and 3 to 600. So from 430 to 600, 640, and 590 minutes. So each operation will be increased. So this will become, okay? So how will this change the affect the total revenue? So with these increases, the only change that will take place in the optimum tableau is the right hand side of the constraints. So we know that the only change that will take place in the optimal tableau is the right hand side of the constraint. And we can use this to get the new right hand side of the tableau for the optimal iteration. So that's what we're going to do here. So we have x2, x3, and x6 be equal to the inverse at that point of the tableau. And I'm gonna allow you to use the calculator in the exam, just in case that you need to compute something like this. You don't have to do it by hand. So if you want to bring your calculator, you can bring it to the exam. 140, 320, and 30. So since these are positive, the current basic variables x2, x3, and x6 remain feasible. Okay, so feasible basically means that you are satisfying the constraints. Since you know that x1, x2, and x3, all your variables need to be positive or greater or equal to 0. As long as they are positive, they remain feasible. Okay, so they stay feasible, and the associated optimum revenue is 3 times 0 plus 2 times 140 plus 5 times 320, and that is equal to this. So increasing the, and this is using the objective function here, so increasing your operations
will increase your revenue. Remember, the revenue was $1,350. Of course, if you have more time or produce more units, your revenue should increase. And that's what you're seeing here. So by increasing the operation time, you're increasing your revenue because you're increasing your production. Okay? Let's look at situation number 2. And I think we're going to have to wait. Let's see how far we can go before, because I need some time to discuss the review. So let's look at this second situation. Although the new solution is appealing from the standpoint of increasing revenue, the company recognized that its implementation may take time. So another proposal shifts the slack capacity of operation 3, in which you have x6 equals 20 minutes, to the capacity of operation 1. How will this change the impact in the optimal solution? So what we're saying here is, let me go back a little bit here. So you know X6 is not part of your production schedule because your production schedule is only defined by X1, X2, and X3, which are your products. You're having a slack variable with the value, positive value here. That slack is consuming part of your resources. What you're trying to do is, since this is not adding a unit of production to your schedule, you want to move that time that you have available, that extra time that you have available, to one of the other operations. So I'm going to move those 20 units in the capacity of operation 3 to operation number 1, which basically is changing your right hand side. So the capacity mix of the three operations changes to 450, 460, and 400. So you're moving 20 units from operation 3, so it used to be 420, you're taking 20 units and you're putting those 20 units here in the first operation. So that's why this becomes 400 and this becomes 450. So the resulting solution is, let's do the same procedure, x2, x3, and x6. Take the inverse from the optimal tableau. Times the new right hand side, 450, 460, and 400, and this will become this 230 minus 40. Is that solution feasible? It's not feasible because x6 is less than 0. Okay, so there's a variable that is not positive. So the resulting solution
solution is infeasible because x6 is less than 0. Okay, so from here you can find the optimal solution for having this right hand side. What this is telling you is that the current solution is not feasible. But that doesn't mean that you can find an optimal solution for that problem. The issue is, in order to find this, you need to perform a set of computations, basically an adaptation of the simplex algorithm. For the purpose of this class, we are not going to be dealing with that part of the simplex method, but we're going to have a new course coming up next semester in which those topics are going to be covered. What its goal is, you can come up from here, at this point of the tableau, you can find an optimal solution using what is called the simplex dual algorithm. But again, that's not part of this class. It's very time, requires a lot of time. So that's why we have that part of the course in this new course that is going to be taught by Dr. Wall next semester. So if you're interested in this type of stuff, you can always take that class. So I guess there's more people that are considering now part of, well, if you enjoy math, and again, this type of material is difficult, it's hard, but if you are one of the few who master these type of topics, then you're going to separate yourself from most of the industrial engineers because it's hard. Not a lot of people want to go in depth, but if you're able to master these topics, then you will be able to get a lot of opportunities in the job. Okay, so that will open your doors to rail companies.